Welcome back to the Institute of Astronomy. So every week, while we are all self-isolating at home, we're putting out this series of astronomy talks, so we can learn some really fun and cool things about space in the meantime. I'm really excited about today's talk. This is one of my favourite topics in all of astronomy. So this talk is all about the dark universe, and it really gets to the heart of what I really love about astronomy. It's the astronomy as solving mysteries and answering really big questions. It's some really cool stuff. So just as every week, this is going to be an interactive astronomy talk. So it's going to be interactive in two ways. So you guys are going to have the chance to ask me some questions, and I'm going to be quizzing you as we go along and testing your astronomy knowledge. So the way this is going to work, as always, we are going to be using Slido, and I can see some questions coming in already, which is absolutely amazing. So the way you can join in the conversation is go to slido.com. So with a phone or some kind of internet device, type in slido.com and use the code DARK, or even easier, just scan that handy QR code in the top left-hand corner. And that way you can join the conversation, so you can participate in the couple of quizzes that we're going to be doing as we go along. But more importantly, you can ask me some questions, as these people are doing already. And then at the end of the talk, there's going to be a question and answer session where I will do my best to answer all of your dark matter, dark astronomy questions that come up as we go along. So like I said, this is the dark universe, one of the most exciting things in astronomy for me, definitely one of the most interesting topics that I know of. And it's going to be something of a scientific detective story. Because if you think about it, being a detective is really what being a scientist is all about, right? As a scientist, it's your job to find mysteries in the universe and then go around looking for clues to solve these mysteries. And so when you're an astronomer, what you have to do is you have to look for strange mysteries in the universe and then try and find clues and pieces of evidence that you can put together to work out what's going on and explain the weirdness that you found. And what I'm going to be talking about today is one of the biggest mysteries of all in astronomy. It's this: most of the universe seems to be missing. So this is the mystery that I'm going to be talking about today. This is the heart of the scientific detective story that I'm going to be introducing. This is why I love this topic. It's this really big, exciting question. Where is most of the universe? It's the classic detective story, right? Something's missing. We have to work out what's going on. And as well as being a detective story, I should also say right up front that this is an unsolved detective story. We know that there is a big problem, that most of the universe seems to be missing. We are doing our best to try and work out what's going on, but right now we don't really know the full answer. So yeah, spoiler for the end, I'm not going to be telling you the answer because we don't know the answer yet. So this can also be a kind of a cry for help for young people that want to grow up and become astronomers. Maybe you guys can grow up and become scientists and help us solve these problems. It's going to be a talk in two halves. Originally it was going to be two halves today, but it's quite a lot of stuff, so we're going to do half this week and half next week, because there's two different types of missing stuff. There's a bunch of missing stuff that seems to glue the universe together, and there's a bunch of missing stuff that seems to be doing the opposite, blowing the universe apart. So that second one we're going to handle next week. Today we're going to be talking about all this strange invisible stuff that seems to be holding the universe together, and it's going to be the detective story of how we are going about trying to find this stuff. Okay, so let's forget universes for a second, because it gets very complicated, or it gets quite abstract quite quickly, and let's think of a much simpler question. How do you weigh yourself? If you wanted to find out how much that you weigh right now, what would you do? I'm guessing you probably have some scales in your house, and so you would go and dig the scales out, and then you would stand on those scales, right? And then whatever number shows on the scales is how much you weigh, okay? Pretty simple, right? But think about what's actually happening. Like, why do the scales give you a number? And it's because you're being pulled down by gravity, right? So when you stand on the scales, gravity pulls you down, and then the number that shows on the scales is how much gravity is pulling you down, right? It's a number that represents how strongly gravity is pulling you down towards the Earth, right? So gravity is something that we use when we want to weigh things, and that's what I'm going to be talking about for a bit, how that gravity can be a really useful tool for weighing things. What about if we go other places in the universe? So think about the moon, right? So this is this nice video that NASA released of astronauts happily jumping around on the moon. And you can see that everything looks a bit floaty, doesn't it? When the astronaut jumps up in the air, they take a bit of a longer time to go down. So that's a bit of a hint that gravity is behaving differently. And so we're going to come to the first of today's quiz questions, which hopefully is quite an easy one to start you off. Is gravity on the moon stronger or weaker than the gravity on Earth? So the gravity on the moon is definitely different to Earth. Is the moon's gravity weaker or stronger than the Earth's gravity? Hopefully this will be a nice and easy one to get you started. So I'm going to give you a little moment to have a think about that. I can see lots of fantastic questions coming through already, by the way. So yeah, keep these coming. I might not be able to get to them all because there are absolutely loads of them coming through, but I will do my best to answer as many of these really, really fantastic questions as I can at the end of the talk. Okay, is the gravity on the moon stronger or weaker than on the Earth? Let's see what you're saying. Very nice. 99% of you, almost everyone, has got exactly the right answer. The gravity on the moon is weaker than the gravity on the Earth. Very, very nice. Well done, you guys. And so the gravity on the moon is weaker than the Earth. If you could take your scales to the Earth and if you take your scales to the moon and stand on them, you would find that the gravity on the surface of the moon is about 1/6 of the gravity on the Earth. So you weigh 6 times more on the Earth. So it's a nice way to lose weight easily, right? If you could stand on the moon, and you would weigh 10 kilograms if you weigh 60 kilograms on Earth. And so because the moon's gravity is less, because the moon has weaker gravity, things like fall more slowly as well. For example, if you imagine dropping a couple of weights, dropping a weight on Earth and dropping a weight on the moon, if you drop them at the same time, like now, the weight on the Earth is going to fall much faster, right? Because gravity is pulling it down harder. And so the point I'm trying to make is that because the moon's gravity is weaker, we know that the moon has to weigh less than the Earth, right? Think about what causes gravity. Like gravity comes from the fact that the moon weighs something. And so in general, if we want to know how heavy something is in space, what we have to do is see how strong its gravity is. This is what I was talking about when I was saying gravity can be a tool to weigh things. If we want to weigh something in space, what we do is we see how strong its gravity is, and that lets us weigh things in space. So what else can we weigh in space? Let's find some other things. What about the sun? Right, so the sun is the star in the center of our solar system. This is a video that I showed way back in week 1 of these talks. It comes from this fantastic YouTube channel, Solar System Videos, and it shows this nice cartoon of the planets in our solar system orbiting the sun. So remember, the colored lines aren't there, right? They're just showing you how the planets are pulled around by the gravity of the sun. And the gravity of the sun is the important thing, right? If it wasn't for the gravity of the sun, all the planets would just fly off into the darkness of space. It's the gravity of the sun that holds the solar system together. So can we use this gravity to work out how heavy the sun is? And the answer is yes, right? We can't put the sun on a giant pair of some giant cosmic scales to weigh it. But what we can do, we can use the same gravity trick and look at how strong the gravity is and use that to weigh the sun. Okay, so time for the second quiz. This one is a little bit more tricky. If the sun was bigger, like had stronger gravity, would the Earth be pulled around the sun faster, or do you think it would go slower? So this can't happen in real life, right? So we're kind of pretending that we have magic power. Say you have a magic astronomy wand and you could make the sun bigger and give it stronger gravity. Do you think we would speed up, or do you think we would slow down? Kind of cool space fact for you while we're waiting. The Earth goes around the sun at more than 60,000 miles an hour, which is the most incredible fact to me. So it doesn't feel like it, does it? If you shut your eyes right now, I guess after you've voted, shut your eyes and you can know that you're traveling right now at more than 60,000 miles an hour around the sun. It's amazing that we could be traveling so fast without realizing it. Okay, let's see what you guys are saying to this one. This one is a bit more tricky. But yes, 3/4 of you have got exactly the right answer. Well done. If the sun was bigger, has stronger gravity, then the Earth would be pulled around faster, which kind of it makes sense if you think about it, right? If you think of gravity like being the strength of something, if you're stronger, you can move things around easier and move things around faster. So with stronger gravity, Earth would be pulled around the sun much faster than we are at the moment. So yeah, we're going at this at 60,000 miles an hour or something a bit more than that. If we can make the Earth bigger, if we can make the sun bigger, we would speed up. If we can make the sun smaller, we would slow down. But the speed we're going gives us the weight of the sun, and that turns out that is about 1,000,000 times heavier than the Earth. And we know that because of its gravity, right? We didn't get some giant cosmic scales and put the sun on it. We just measure the strength of its gravity. And luckily, this works for everything in space. So whenever you find out that astronomers have weighed something in space and we say this is how much something weighs, this is how we work it out. We just look at the gravity. So we can weigh the moon, for example, by taking a spaceship that's going around the moon, and we just look at a spaceship orbiting the moon, and depending on how fast that spaceship is going, we can use what we know about gravity to weigh the moon. So that's how we know that the moon is about 100 times lighter than the Earth, right? The Earth is 100 times heavier than the moon. We know that because of measuring the gravity of these things. Pluto is another cool one, right? So Pluto, when it was first discovered, we didn't really know how much it weighed. It was a bit of a mystery. It was just this teeny tiny dot on the edge of the solar system. How do you weigh a teeny tiny dot? Well, we kind of can't, right? But we were able to weigh Pluto when we found out that Pluto has a moon called Charon, and we can watch this moon going around Pluto, measure the gravity of Pluto, and then that tells us how much Pluto weighs, which is about 5 times lighter than the moon. So this trick is amazing. We can just weigh something that's like billions of miles away in the solar system. Venus is a really, really interesting one. So Venus doesn't have any moons, so you'd think it would be quite difficult to work out how heavy Venus is. But it doesn't always have to be a moon. You can just look for things like asteroids and meteorites. So when little meteorites go past Venus, we can watch them being tugged around by Venus's gravity. Then that tells us how strong the gravity is on Venus, which tells us how much Venus weighs. And so we know that Venus weighs about the same as the Earth. So this is great. We have a trick that we can just look at the gravity of something and it lets us weigh things. And so we can weigh stars, we can weigh planets, we can weigh all kinds of things in space. What about bigger things? Do you think we can go bigger and weigh something else? So what about a galaxy? So galaxies are really cool things. Again, I spoke about these in week 1. We're part of the Milky Way galaxy. The sun is just one of about 200,000 million stars in our Milky Way. And galaxies, just like the solar system kind of rotates with all the planets going around the sun, galaxies rotate as well. Galaxies are big spinning things in space, and so the sun is being pulled around by the gravity of the Milky Way, just like the Earth is being pulled around by the gravity of the sun. They take a long time to go around, so the Earth does a lap of the sun in a year. The sun does a lap of the middle of the Milky Way in about 220 million years, so it takes a lot longer to go around. But even still, we should be able to use our trick, right? We should be able to look at stars in a galaxy, measure how fast they're being pulled around, and that lets us weigh a galaxy, which is an amazing thing if you think about it. This giant thing, millions and millions and millions of miles wide, containing hundreds of thousands of millions of stars, we can just work out how much it weighs. So we do the trick. So this is the Andromeda galaxy. That's the nearest big galaxy to our Milky Way. We can just look at a bunch of stars, look at how fast these stars are being pulled around, and that lets us weigh the galaxy. We can use our gravity trick again. Easy, right? Well, no. Unfortunately, at this point, we hit a very, very interesting problem, and this is where today's topic comes in. The problem is this: galaxies are a lot heavier than they look. And by a lot, I mean like a lot heavier than they look. So what does this mean? What does it mean to say that a galaxy is heavier than they look? Well, you can take a look at this galaxy, right? Or take a look with a telescope and look really carefully, and you can get a rough idea of how many stars are in our galaxy, right? Like I said, our Milky Way has 200,000 million stars inside it. So you can look at a galaxy and get a rough idea of how many stars are inside it, which should give you a rough idea of how much it weighs, right? Galaxies are big clouds of stars. You count the stars and you've pretty much got a rough idea of how much the galaxy weighs. But it turns out that's just completely wrong. When we use our clever gravity trick, it turns out that galaxies are way heavier than they should be. which is really, really odd. It's kind of like you're weighing something very light, like you're putting a mouse on a pair of scales, and then your scales tell you that you're weighing something very, very heavy indeed. That's weird. That tells you that there's something wrong here, or there's something very strange going on that we don't expect. So galaxies are about 10 times heavier than they look, which is a huge amount, right? So if this is how heavy galaxies look, this is like a representation of how heavy galaxies actually are. So like 10% of a galaxy's weight is absolutely fine. That's the stuff we can see, that makes sense. But most of a galaxy seems to be this weird invisible stuff that we know it's there because we can see its gravity, we know it weighs something, but we just can't see it at all. So what is this stuff? Why are galaxies full of this weird invisible stuff that seems to weigh something, but we just can't see it? And this actually gets worse than that. So I've been talking about different things in space, and I've said that galaxies act weirdly. It's not just galaxies that act weird. It's actually everything. Whenever we put our telescopes to anything in the universe, with anything big, so we look at galaxies or clusters of galaxies, or even the entire universe itself, we see this exact same problem. We see that everything is heavier than it should be. So this weird, like, invisible stuff that seems to be weighing down galaxies, that seems to be absolutely everywhere. The whole universe is much, much heavier than it looks. It looks like there's a bunch of invisible stuff in the universe. We know it's there because we can see the gravity of it. We can see that it weighs something, but we can't see it at all. So what's going on? What is this stuff? And the answer is, we don't really know. It's a mystery. This is why I call this a scientific detective story. We know this stuff exists. We really don't know what it is. Our best, so what we call it is dark matter, right? So matter here means that it's stuff, it's some stuff that's out there. So matter is just a scientific word meaning stuff, right? Like I'm made of matter, you are made of matter, your house is made of matter. Matter just means stuff. So dark matter is stuff that's there, but it's invisible. That's why we say it's dark. So dark matter is invisible stuff. We know it's there because we can weigh it. We can't see it. So we know we live in a universe full of dark matter. And our best guess, so this is a kind of a nice drawing of just some kind of spooky little thing. Our best guess is that dark matter is some kind of teeny tiny particle, so much, much smaller than an atom, right? So our best guess is that the universe is full of just an absolutely ridiculous number of these tiny, tiny particles, like a whole sea of these tiny particles that is just filling the universe. And that's our best guess at what dark matter is. We don't really know what these particles are or how they work or anything like that, but that's just from looking at the universe, that's our best guess for what's going on. So why is dark matter dark? Like if the universe is full of these particles, why can't we see them, right? If there are so many of them, you'd think we should just be able to look around and they should be everywhere. Why is dark matter dark? So let's think about how you see anything at all. How does looking at stuff work? So say you want to see an object like a cat or something. You need some light to be able to see things. And the way you look at things, the way you see things is that light comes, like reflects off them, right? So light from the sun will come down, hit an object, reflect off it and go into your eyes, and then you can see that thing. Or, for example, you're looking at your computer screen now, right? The way you can see this picture I'm showing you is because light is coming out of your computer screen and going into your eyes. Look at the wall next to you, right? The reason you can see that wall is because light is bouncing off the wall and then going into your eyes. If you look really closely at what's going on, right, let's zoom in. So what's happening? You have some object, and then you have like bits of light called like photons or waves of light that are coming down, and they are crashing into the object and bouncing off. Right, this is what reflecting is, right? That light hits the object and bounces off. And so that's how you see things, right? If light didn't bounce off this object, if light just kind of passed straight through it, then we wouldn't see it. It would be invisible. You need reflection to be able to see things, right? You need light to be able to bounce off something, and then that's how we see something. And so this is why we think dark matter is invisible, because light doesn't bounce off it, right? So if you have a dark matter particle, some light will just happily go straight past dark matter as if it's not even there. And that's why this stuff is invisible. So that there can be loads of these dark matter particles out there in space, but any beams of light that go past them just go straight through and out the other side as if they're not there. And so because dark matter doesn't interact with light at all, that's why it's invisible. That's why this stuff is so hard to see. And by light, of course, I don't just mean the light we can see. I mean stuff like radio waves or infrared or all of the types of light that we use to study the universe. Dark matter ignores all of it, which makes it really, 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 or makes it impossible to see. So dark matter doesn't just ignore light, it ignores pretty much everything else as well. Like dark matter is the original social isolator, right? Dark matter avoids pretty much everything else. And one of the things that dark matter ignores are atoms. So remember, we were talking last week about how atoms are mostly empty space, right? So atoms have a nucleus, the little dot in the middle, and some electrons, but most of atoms is just empty space, right? 99.9999999% empty space, right? Dark matter can just waltz through that empty space as if the atom isn't there. So because atoms are almost entirely empty space, dark matter just happily passes through and out the other side as if atoms aren't there. Dark matter just passes through atoms really, really easily. Which also means that dark matter can just pass through anything that's made of atoms. So like the Earth is made of atoms, dark matter can just go through the Earth and out the other side. So this is why it's hard to find, right? We can see that space is just full of this dark matter everywhere, but it's like rain. It just kind of streams through the Earth and out the other side. And that's true of anything made of atoms as well. So like, we're made of atoms. My body is made of atoms. Your body is made of atoms. And so dark matter can just go straight through your body and out the other side as if it's not even there. And so we now think, or we're now almost certain that there are billions of dark matter particles passing through your body right now. There's so much dark matter out there in space. It's just streaming through your body right now. So if you put your hand out and look at your hand, like there are billions of dark matter particles passing through your hands, like this very second. But from a dark matter's point of view, like you barely exist, right? You're just they just go through you and out the other side as if you're not even there. So how can we find out what this stuff actually is? Right, we can see this stuff out there in space. We know it's there because we can see its gravity. How can we find out what it actually is? So what we want to do is build some kind of machine that can detect dark matter. We want to be able to find it so we can learn more about it. And so what we do, we go deep underground. So we dig big tunnels, or more often than not, we use tunnels that are already there, right? We go down into big mines, and then deep underground, we build machines that can detect dark matter. And then the idea is that if a dark matter particle comes along, it can just pass through the Earth as if the Earth isn't there, because that's what dark matter does. And then when it hits our machine goes ba-ding and detects the dark matter, and then we can say, great, we found it. The reason we go underground is because there's all kinds of particles flying around all the time, right? Like the sun spits out cosmic rays, but most of these particles just can't go through the ground, right? That's something that like pretty much only dark matter can do. So most of the stuff from space just hits the ground and bounces off. And then so if you build your dark matter detecting machine deep underground and you find something, you can be pretty sure it's dark matter, because only dark matter can kind of happily waltz through the Earth as if it's not there. So this is what we do, right? We go deep underground, we build these dark matter detecting machines to try and catch some of these dark matter particles as they just kind of waltz through the Earth. This is a picture of one of them. They look super cool. This is one of these dark matter detecting machines that's down in Italy. It looks like some super sci-fi spaceship, or doesn't it? So this is one of these things that's deep underground and is trying to detect these dark matter particles. There are lots of these all over the world. They all have kind of different designs, but they have one thing in common, which is that so far, none of them have been able to detect dark matter. So far, we haven't found any of this stuff. And if you think about it for a second, the reason why is kind of obvious, right? So if dark matter has this weird power that it can just pass through atoms as if it's not there, it can pass through the Earth, it can pass through my body. It means it can also just pass through any machine that you build to detect dark matter, right? So if a dark matter particle can go through atoms, any machine or detector you build to try and catch dark matter is also going to be made of atoms. So dark matter can just happily go through the machine and out the other side, and you're not going to find anything. It's a bit like, an easy way to explain it is, imagine that you're building a dark matter detector, which is like a net that you want to catch some dark matter in, and then dark matter particles are like tiny, tiny things that are much, much smaller than the holes in the net, right? Like trying to catch a fly in like a tennis net or something. It can just happily go through the holes and you can't catch anything. So that's what's happened so far, right? We've built these dark matter detectors, but so far they just haven't been good enough. The holes in the net have not been small enough to catch a particle of dark matter. And so what we're trying to do, we're trying to build better and better dark matter detectors, make the holes in the net smaller and smaller, so eventually we're hoping we can catch one of these particles. But it's very, very difficult, and we haven't been able to do it so far. So even though dark matter is very strange, and even though we don't know that much about it because we've never been able to catch one of these particles, we don't really know what they are. But what we do know is that dark matter is really, really important. Because if it wasn't for dark matter, the universe as we know it would not exist. So this is a simulation of a universe. This is a toy universe that astronomers build inside a computer. So this is a program called Illustris. It's a model universe running inside a supercomputer. And all of the blue stuff you can see here is dark matter. This is a really, really big chunk of the universe. Every tiny little speck is like a galaxy. And all of the blue stuff is the dark matter. And what we've worked out from our models of the universe is that if you don't have dark matter, the universe as we know it doesn't form. Like dark matter provides like the skeleton of the universe, if you like, or the scaffolding of the universe. So dark matter kind of clumps together and forms structures, and then the rest of the universe, what we think of as the real universe, forms around it. Dark matter comes first and provides the scaffolding for the entire universe. So when we look around and we see planets and stars and the planet that we're living on, galaxies out there in space, none of it would exist if it wasn't for dark matter. So even though this stuff is very, very strange and very, very spooky, it's really, really important. It's only because of dark matter's existence that the universe as we know it exists at all, which I find absolutely amazing. Okay, I think so that is a good place to end. So dark matter, very, very interesting. We know it's there. We don't know what it is, but we do know it's very, very important. And the universe only exists because of dark matter. So what I want to do now is switch over to some of your questions. Where are we? Here we go. Okay, questions. 188 questions. I'm going to do my best to answer a few of these. We've got about kind of 15 minutes or so. Okay, so where, and Anonymous asked, top question, where would a compass point if you are in space? So most likely a compass wouldn't do anything if you're in space. So what compasses on Earth do is follow the magnetic field of Earth. So the needle of the compass points to the north of Earth because it's being manipulated, it's being moved around by Earth's magnetic fields. There are magnetic fields in space, but generally they're much, much, much weaker than when you're near a planet. Because being on the surface of a planet, we are next to a big ball of iron, right? The Earth's core is made of iron. We're basically standing on a big magnetized ball of iron. So the magnetic field right here is stronger than in most places in space. So generally, if you're in space, a compass just wouldn't point anywhere because the magnetic field is not strong enough. But if you were close to something with a very strong magnetic field, like stars have magnetic fields, or neutron stars, pulsars have very, very strong magnetic fields. And if you were near one of those, then the compass would point towards the thing with the strong magnetic fields. Malachi says, could the dark side be hiding out in the dark universe? I don't know what you mean by the dark side. I don't know if you mean dark side in some kind of Star Wars way. But it is the idea of there being this dark universe is interesting. So one idea is that there might actually not be just one kind of dark matter. There might be a whole range of dark particles. There might be a whole dark universe out there made of all different things that we can't quite detect. So right now, almost any question about the dark universe, one of the answer has to be, we don't really know yet. We're doing our best to find out about dark matter. We know little bits about it. We know what it does. We know how it forms our universe. But what dark matter actually does, there's lots of mysterious things so far. Great question. I bet I could answer. I wish I could answer better. Aprigit asked a couple of fantastic questions. So first of all, why is such a large percentage of the mass of the asteroid belt in Ceres? Why wasn't it able to accrete into a bigger planet? So the asteroid belt, of course, this ring of rocks in our solar system between Mars and Jupiter, and Ceres is the biggest thing in the asteroid belt. But even still, the asteroid belt taken as a whole isn't actually that heavy. If you add up the entire asteroid belt, so not just Ceres, but all the other stuff as well, you would only get to about 10% of Earth's mass. But we think the reason the asteroid belt couldn't coalesce into a bigger planet, like why don't we have just a planet that's 10% of Earth's mass instead of the asteroid belt? Our best guess is that it's because of Jupiter's gravity, right? So I don't think it's a coincidence that the asteroid belt is next to Jupiter, the biggest planet in our solar system. Jupiter's gravity is strong enough to disrupt planet formation around it, and so that's why the asteroid belt was never quite able to coalesce and form a planet, which is quite useful. It means the asteroid belt is a nice relic of the early solar system, because it's all the stuff that didn't quite manage to make it into a planet. But yeah, the answer is Jupiter's gravity. Aprojat also asks, why do binary star systems outnumber single stars by such a large extent? So this is a really good question. So our star is a single star, like our sun is a single star, but binary stars, so stars where there are two stars going around each other, are actually more common. So why is this? The answer is to do with something called angular momentum. And so we spoke a few weeks ago about how stars form, right? You start off with a big cloud of gas in space, and then gravity shrinks this cloud of gas down smaller and smaller and smaller. Then eventually it gets small enough and hot enough to turn into a star. As things get smaller, they start spinning faster. It's a trick that ice skaters use, right? So if you see people doing ice dance, they'll start spinning with their arms out, and then they'll make themselves smaller. They'll pull their arms into the body, and that will make them speed up and spin faster. You can do the same trick on a computer chair. If you sit on a spinny chair and spin around, and then kind of pull all your arms and legs into your body, you'll find yourself spinning faster. And so that's what happened to the gas clouds. That's if a gas cloud is collapsing down to form a star, it's going to get smaller and smaller and start spinning faster and faster and faster. When it gets very small indeed, it tends to be spinning quite fast, and so it can often be spinning fast enough that the centrifugal force kind of breaks it up into two bits, and you end up with two stars forming. So the answer is really that because things spin faster and faster and faster as they get smaller. More often than not, when something gets small enough, it's spinning so fast that the centrifugal force tears it into two, and you end up with two separate stars. So that's why binary stars are more common. Amelia, age 10, and Hugh, age 6, says, how do we know that dark matter exists? That's a really, really good question. So I talked about the evidence for dark matter, right? So the fact that it looks like galaxies weigh a lot more than they look like they do, right? So when we look at a galaxy, we have one measure of how much it weighs just from kind of looking at it, and we have another way of measuring how much it weighs from this gravity method. And our gravity method, the galaxy weighs way, way, way more than it looks like it weighs. And so one of two things is wrong, right? So either there's loads and loads of invisible stuff that we can't see, which is dark matter, or the other option is that we don't quite understand gravity properly, right? So it has to be one or the other. Either dark matter exists or we don't understand gravity properly. We astronomers are almost certain the answer is that dark matter exists, because whenever we look all the way around the universe, we look at all different things. It's not just galaxies. Everything we look at in the universe, we get the same answer, that there's all this weird missing stuff. Everything in the universe seems to weigh more than it should do. And so that's what we think dark matter is. It's this stuff that's all the way around the universe, and we can see the gravity of it everywhere. And so just because we haven't found what it is yet, it doesn't mean it doesn't exist. So we know that it exists because we see it absolutely everywhere. Slido Man says, if dark matter makes up around half the universe, what's the other half? So dark matter doesn't really make up half the universe. So out of the kind of the matter, the stuff in the universe, dark matter is about 85%. And what we think of as normal matter is about 15%, which is amazing if you think about it, right? I think it's because we are made of normal matter. I think we get quite biased in the other direction. We tend to think of what we're made of as the real stuff in the universe. and dark matter is this kind of weird, spooky extra stuff. If anything, it's the other way around, right? Dark matter, 85% of the universe, that's the normal stuff, right? We're the weird exception. We're like this 15% small stuff. So dark matter, out of matter, dark matter is about 85%, and the remaining 15% is just normal stuff, like what me and you and the stars and the planets are made of. There's also this stuff called dark energy, which we're going to talk about more next week. That's the other half of today's talk. So the dark universe is made of dark matter, which is what I'm talking about today, but there's also lots of dark energy in the universe, which makes up a lot of the universe as well. Where are we? Aprojat. Oh, you asked so many good questions, Aprojat. I'm going to answer some others from other people before we get to some of your questions. Joe says, "What's the weirdest thing you know of in the universe?" That's a difficult question. There are lots of very weird things in the universe. I think probably the weirdest thing in the universe has to be black holes. Black holes are so weird. They really stretch our understanding of the laws of physics to almost breaking points, right? So black holes are... The reason I think they're so weird is you take an entire mass of a star and you squash it down into an infinitely small dot. So a black hole is a tiny, tiny speck that can weigh as much as a star, or even in the case of a supermassive black hole, can weigh billions of times as much as a star, which for me is the weirdest thing in the universe. A tiny speck, smaller than an atom, that weighs billions of times as much as a star. I find it almost impossible to understand, but we know they do exist. So I think that has to be the weirdest thing in the universe. All right, if I take that one off. Yes, Aprojat asks, what is the cause for the deviation of Neptune from its expected orbit? So the expected orbit is how we think that things should be behaving according to the laws of gravity, right? So we know how gravity works, and we can kind of plot how different planets should be orbiting the sun according to gravity. But sometimes they don't orbit exactly as they should do, as according to the gravity that we know, and sometimes they slightly move around a bit. And the answer is normally that there is stuff beyond them that's kind of pulling them around. So, for example, Uranus, when the planet Uranus was discovered, it wasn't orbiting where it should do, and so astronomers figured out that there had to be a planet beyond Uranus kind of tugging on it and kind of altering its orbit a little bit. And that was the planet Neptune. That was how we found the planet Neptune. So there are deviations in the orbit of lots of things in the outer solar system. We think that it's most likely it's not just Neptune, it's lots of what we call TNOs, trans-Neptunian objects. And all of these things in the outer solar system behave as if there is a very, very massive planet out there in the darkness of the outer solar system that we haven't found yet. So this gets called kind of Planetnine, right? This because Pluto used to be Planetnine, but now Pluto gets called a dwarf planet. So this mysterious planet gets called Planetnine in the outer solar system. We think it exists because it's affecting the orbit of everything in the outer solar system, but we haven't been able to find it yet. Okay, Tristan and Alexander says, is dark matter on Earth too? Yes, it absolutely is. We know that dark matter is everywhere in the universe, and it is on Earth as well. So this is why we're building dark matter detectors here on Earth to try and be able to find dark matter. So dark matter, if you hold out your hand right now, there is dark matter passing straight through your hand and straight through the Earth and out to the other side. But because dark matter just travels through everything, it's really, really hard to find. So dark matter is on Earth because dark matter is just spread throughout our entire galaxy. Ben and Leone ask, how many stars are there in the solar system? I'm very happy to say the answer is 1. Our sun is a star. It is the star that is in our solar system. Thank you, Ben and Leone. Aprojat again says, okay, I've answered the Neptune one. Why doesn't the dust from the tails of comets accrete to form planets? The answer is there's just not enough of it. right? So the dust in the tails of comets is very, very, very finely spread out. And in order to accrete to form planets, there has to be enough stuff for the gravity of something to pull it all together. The dust in the tails of comets is just far too finely spread out for planet formation to get kind of kick-started. Why does... Oh, this is a great question. Another one from Aprojit. You asked so many good questions, Aprojit. Okay, I'm going to tick off that question because I've answered it. Why couldn't Oumuamua have come from the Oort clouds or due to a collision in trans-Neptunian objects? So for anyone that haven't heard of this, Oumuamua is this fascinating object that came through our solar system a couple of years ago. It was a kind of long, thin kind of piece of rock that was traveling through our solar system. And when we measured its orbit, we discovered that it had to have come from a different solar system. The reason we know it did come from a different solar system and not just from the Oort cloud is because it was something called unbound. So it was basically, so that's a way of saying when we worked out how much energy this object had, there's no way it was kind of attached to our sun, right? So our Earth is bound in an orbit around the sun. The energy of the Earth is such that the Earth just goes round and round and round the sun forever. If you could kind of speed the Earth up, if you can kind of give the Earth like a cosmic kickstart and make it go faster, it could go flying off out of the solar system. And when we measure how fast Oumuamua was going, we found out that it had this amount of energy that it was going so fast it was just flying through our solar system. So there's no way that Oumuamua was in orbit around the sun. It was just going way too fast. It was just passing by, which is how we know that it had to have come from a different solar system. Tristan and Alexander ask, do black holes affect time as well as space? The answer is yes. Space and time are actually two parts of the same thing. It's best not to think of time as being a separate thing from space. So space and time are all part of the same thing. This is how Albert Einstein, one of the most famous scientists of all time, used to think about the universe. And so just as black holes bend space, black holes bend time as well. This is another reason that black holes are the strangest thing in the universe. They make time go all wonky as well. So the answer is a very definite yes. Tristan and Alexander also ask, is there anything past the end of the universe? This is a question that I have to say the official answer is I don't know. We don't know the answer to this. We don't even know if there is an end to the universe. We know the universe goes on a very, very long way. So there's something called the cosmic horizon. So like the horizon on Earth, right? So if you go to the beach and you look out, you can see the horizon on Earth. It's where the Earth curves out of reach and you can't see it anymore. There's also a horizon to the universe. It's very, very far away. It's about 46,500 million light years away. But we can't see anything past that because the light just hasn't had time to reach us, right? So anything that's past that cosmic horizon, the universe just isn't old enough for us to be able to see it. So in a way, we're kind of trapped in a bit of a cosmic bubble. We can't see the whole universe. We can only see to the horizon. So beyond that, the universe might go on forever. We just don't know. So this is a question that I would love to know the answer to, but unfortunately I have to say that no one knows, I'm afraid. Bailey says, does the dark universe continue growing like the universe? And the answer is that the dark universe and the regular universe are all part of the same thing. So the dark universe is stuff that is in our current universe. Right, so the dark matter and the normal matter in our universe are all mixed up together. I called the talk the dark universe because it was kind of cool, but you shouldn't think of it as a separate universe. It's all different stuff in the same universe. So there's only one universe that we are in. There might be other multiverses, but that's a separate conversation. There's one universe we're in, and it contains regular matter and it contains dark matter, and the whole thing is growing. Aprojit also asks, did 2020 HS7 cause any changes to geostationary satellites' orbits? So for those of you that didn't know, 2020 HS7 was an asteroid that had a relatively close encounter with Earth fairly recently. Luckily, relatively close in space still means a very, very long way. So the closest approach of this thing was about 3.5 million miles, if I remember my numbers right, which is still very far away. It didn't even reach between the Earth and the moon. So luckily for us, so it was a near miss by cosmic standards, but it was still millions and millions of miles away, which is much, much, much further away than any satellite's orbit. So yes, we were completely safe. It didn't affect anything on Earth. Finn, age 10, says, is there life in a different galaxy? This is another question I would love to know the answer to. The answer so far is that we really don't know. Astronomers are looking for life very, very hard, but so far the only life that we know about is here on Earth. We do know that the ingredients for life are absolutely everywhere, right? So we are made of a material called carbon. Like we are carbon-based life, and we breathe oxygen, we drink water, and all of this stuff that we think is important for life, like oxygen, like water, like carbon, we see spread out through the whole universe, right? Even in very, 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 very distant galaxies, they have oxygen and water and carbon in them. So we don't know for sure if there's life out there, but I would guess yes, right? If I had to guess, I would say there had to be life out there in different galaxies, because space is a really, really big place, right? There are loads and loads of planets. The ingredients for life are everywhere. I think it has to be out there. We haven't found it yet, but we're looking very hard, and I would guess that yes, we would find it one day. Callum said, when Einstein said there was an observable universe and an unobservable universe, what does dark matter count as if it's in the observable universe? This is a really, really good question. And so the answer is that observable universe and unobservable universe wasn't anything to do with dark matter, right? When Einstein was around, we didn't know about dark matter. That was a later discovery. So the observable universe is the bit of the universe that we can see, right? And that refers to like the volume of our universe. So we look at a galaxy a million light years away. That's inside our observable universe. It's what I was talking about before with the cosmic horizon, right? So we are trapped inside this kind of like this bubble that's about 90,000 million light years wide, and we can't see beyond it. Not because the universe stops, but that's just as far as we can see. So anything inside this is our observable universe. Anything outside this is the unobservable universe. So dark matter is inside our observable universe, and almost certainly outside as well, right? It's just a component of the entire universe. So yeah, it's a bit confusing, right? Because even though it's something that we can't see, observable universe means the bit of the universe that we can see with our telescopes. And even though dark matter is invisible, it's still within this patch of the universe. I hope that makes sense. Chloe says, could the Earth ever be tidally locked with the Sun? So for anyone that doesn't know what being tidally locked is, if two things are orbiting quite close together, they can end up that the time you take to complete one orbit is the same as the time you take to spin around once. And when that happens, you end up having the same face pointing towards the thing at all times. So a really easy example of this is that the moon is tidally locked with the Earth, right? That's why we see one side of the moon all the time, and then there's the dark side of the moon on the other side that we don't see. That's because the moon is tidally locked with the Earth. It would be very sad if the Earth became tidally locked to the Sun, because it would mean there'd be no more day and night, and one side of the world would be in permanent daylight, and one side of the world would be in permanent nighttime, or at least until you waited half a year and they swapped around. So luckily for us, the Earth is not going to be tidally locked with the Sun. We are just too far away. So yes, very happy to say that won't happen. We are going to continue to have days and nights for the future. Where are we? Can dark matter go through black holes? So first of all, I think so. I spoke about black holes last week. If you didn't catch that, you can find that on our YouTube. Things don't go through black holes. Black holes aren't portals. They are just they are just kind of dots in space with very strong gravity that can swallow things. But dark matter can get swallowed by black holes just as much as regular matter. Caitlin says, will the Earth crash into the Sun? Again, I'm very happy to say that the answer is no. Our Earth is just going to happily continue orbiting the Sun for thousands of millions of years to come. Eventually, in about 5,000 million years' time, the sun is going to reach the end of its life and swell up, and then so the Earth will crash into the sun then, not because we've fallen in, but the sun is going to get bigger and bigger and will eventually burn the Earth up. But luckily for us, it's not going to happen for thousands of millions of years, and there's loads of other habitable planets in our galaxy that we could live on, so I'm sure by then humans will find somewhere much nicer to live. Okay, I think that's probably quite a good place to finish. We've been going for about 50 minutes so far. There's 470 questions. I would love to answer them all, but I think I would be here all day. So thank you very much for listening. I hope you've enjoyed this. If you like this talk, you can check out more of our talks in this series on our YouTube channel. If you've enjoyed it, consider giving us a subscribe, and then you'll keep up to date with all of the fun things we're putting out. Like I said, this one today is the first of 2 Dark Universe talks. We've been talking